Picture this. You're walking confidently across a parking lot in winter, and suddenly your feet fly out from under you. You're flat on your back, staring at the sky, wondering why ice is so impossibly slippery. It's a question that seems simple, but the answer has puzzled scientists for over 150 years. You might think you already know the answer. Pressure from your foot melts the ice, creating a thin layer of water. And water is slippery. Case closed, right? Well, here's where it gets interesting. That explanation, believed for decades, is actually wrong. Or at least, it's not the whole story. The pressure melting theory came from physicist James Thomson back in the 1800s. It made perfect sense at the time. When ice skaters glide across a rink, the pressure from their blades must be melting the ice beneath them, creating a lubricating water layer. Scientists taught this explanation in classrooms worldwide. There was just one problem. The math didn't add up. Let's break down why this theory fails. To melt ice through pressure alone, you'd need enormous force. A typical ice skater generates about 50 times less pressure than required to actually melt ice at typical winter temperatures. If pressure melting were the answer, ice skating wouldn't work at -10 degrees Celsius. But it does. People skate in -30-degree weather without any issues. So what's really happening? The answer lies in something called the quasi-liquid layer. Even when ice is well below freezing, its surface isn't completely solid. The molecules at the very top of the ice behave differently from those locked deep inside the frozen structure. They're more mobile, more disordered, existing in a state between solid and liquid. Think of it like the surface of a crowded dance floor. In the middle, everyone's packed tight, barely able to move. But at the edges, people have more freedom to shift around. Ice molecules work similarly. The ones on the surface lack neighbors above them, so they're less rigidly bound. They vibrate and move in ways that create a slippery, water-like layer just a few molecules thick. This quasi-liquid layer exists on ice even at -35 degrees Celsius. It gets thicker as temperatures rise closer to freezing, which is why ice becomes more treacherous near 0 degrees. The warmer it gets, the more liquid-like this surface layer becomes, and the easier it is to slip. But here's where it gets even more fascinating. Friction also plays a crucial role. When you walk or skate on ice, the friction generates heat. This heat does melt a tiny amount of ice, adding to the quasi-liquid layer already present. So the old pressure melting theory wasn't completely wrong. It just had the mechanism backwards. It's not pressure doing the melting, it's the heat from friction. Scientists only confirmed this explanation relatively recently, using advanced microscopy and computer simulations. In 2019, researchers at the Max Planck Institute actually observed these surface molecules in action. They watched the quasi-liquid layer form and change thickness with temperature. It was like finally seeing the invisible force that had been tripping people up for centuries. This discovery has real-world applications beyond explaining your parking lot tumble. Understanding ice slipperiness helps engineers design better winter tires and runway de-icing systems. It explains why some materials stick to ice while others slide effortlessly. It even matters for climate science, since this surface layer affects how ice crystals form in clouds and how glaciers move. Here's a fun fact. Not all ice is equally slippery. The quasi-liquid layer thickness depends on the type of ice crystal structure. Some forms of ice found on other planets or in laboratories don't have this property at all. They'd be much safer to walk on, though you'd have other problems to worry about. The slipperiness of ice also changes with what's dissolved in it. Salt disrupts the crystal structure, affecting the quasi-liquid layer. That's another reason why salting roads works beyond just lowering the freezing point. So next time you're carefully navigating an icy sidewalk, Remember, you're experiencing quantum physics in action. Those surface molecules, dancing in their quasi-liquid state, are the reason winter walking requires such caution. What seemed like a simple question about why ice is slippery turned out to reveal a complex dance of molecular physics, friction, and surface chemistry. It's a reminder that even the most everyday phenomena can hide extraordinary science just beneath the surface. What other simple questions might have surprisingly complex answers hiding in plain sight?